Hi everyone, welcome back. This is going to be the final video for section 16.5, and the first part of this video we're going to talk about surface area of implicit surfaces. So what if you have some implicit surface, meaning a function of three variables set equal to some constant, and it's difficult to come up with a parameterization for that surface. It's not entirely obvious what you should do. We can still find the surface area of this surface, and we're not going to need the parameterization. So let's go through how that's possible. What we're going to do is use the implicit function theorem and assume that we can write z as a function of x and y. Now we're never actually going to find this h function, but let's assume for the moment that we can. Okay? So then what do? If we have z equals a function of x and y, then we can do what we did in the very first video for this section. We can say, okay, x is a parameter, y is a parameter, and then this third component is just my function. So we saw this in the last video, but really this is what we did in the first video. And now u and v are in some domain D. D is going to be in the xy plane because this is really x, this is really y. So these are, D is going to be wherever x and y take value. So whatever portion of the xy plane we're integrating over. Okay, now if I take partial derivatives of this parameterization, the partial derivative with respect to u is 1, 0, partial derivative of h with respect to u. The partial derivative with respect to v is 0, 1, partial derivative of h with respect to v. And remember, we're not actually going to use h. We're going to rewrite these partial derivatives using the implicit function theorem and write them in the same way that we did back in chapter 14. So we're going to replace the partial derivative of h with respect to u. Remember, h is really z, u is really x. So this is negative partial derivative of capital F with respect to x divided by the partial derivative of capital F with respect to z. We do the same thing. We replace the partial derivative of h with respect to v. Remember, this h is really z, this v is really y. So we replace that with negative the partial derivative of capital F with respect to y divided by the partial derivative of capital F with respect to z. So now we can compute this cross product, plug in these representations of the partial derivatives, and we compute the cross product, and we get this vector. And now I'm going to take this vector and I'm going to factor out 1 over the partial derivative of f with respect to z. And here I have to put the partial derivative of f with respect to z, so that if I distribute this back through, I get 1. But now this vector is just the partial derivatives of this capital F function. That's exactly the gradient. So this cross product is the gradient of this capital F function divided by the partial derivative of this capital F function with respect to z. And so in this way, we never actually have to find a parameterization. We can just use that implicit function, this function of three variables, take its gradient, divide by the z partial derivative. So then when I want to find surface area, if I were to take the magnitude of this cross product, it's just the magnitude of the gradient divided by the absolute value of this z partial derivative. It's important to be aware that these vertical bars mean two different things in these cases. Around a vector, which the gradient is a vector, we're taking the magnitude, and in the denominator, this is a function, we're taking the absolute value of that function. So then the surface area of an implicit surface, so some function of three variables equal to a constant, can be found by this integral, where we're integrating the magnitude of the gradient over the absolute value of the z partial derivative. And D is a region in the xy plane. So here we're integrating with respect to x and y, unless you need to convert to polar or something like that. I would say, of all the different formulas we looked at for surface area, I would keep this as a last resort. And one of the reasons is, if you're taking these partial derivatives, what happens if you have a z in here? We're integrating with respect to y. If I end up with z's in here, I'm going to have to find some way of representing z anyway. So it's best practice is see if you can find parameterization in u and v. So now let's take a look at an example of how we could use this. So find the area of the plane x plus 2y plus 2z equals 5 above the region bounded by x equals y squared and x equals 2 minus y squared. So the first thing I want to do is look at this region in the xy plane and figure out what our bounds of integration should be. So here's kind of everything all at once, and we can go through it. So I've drawn these two parabolas. X equals y squared is this red parabola. X equals 2 minus y squared is this blue parabola. And then the region between them is here. So this is the region that we're integrating over. I'm going to need to know what these points of intersection are. Where do these two parabolas intersect? So I can set the equations equal to each other. They're both solved for x, so that means y squared has to equal 2 minus y squared at these 2 points, because that's where the curves intersect. I solve that, I'm going to get y equals plus or minus 1. So those 2 points are 1, 1, and 1, negative 1. So those are the 2 points of intersection. And now I want to come up with bounds for this region. So you need to decide, do I want to integrate with respect to y first, or do I want to integrate with respect to x first? And in this case, we do not want to integrate with respect to y. Why is that? Because if you look here, y is bounded by this red parabola over here. But over here, y is bounded by this blue parabola. So if we integrate with respect to y first, we have to set up two separate integrals. One integral for this region, where it's bounded by the red parabola, top and bottom, and one integral for this region, where top and bottom is bounded by the blue parabola. But if we integrate with respect to x first, and we go from left to right in this region, I'm always starting at the red parabola, I'm always going to the blue parabola. So I only need one integral because x is bounded below by y squared, that's the red parabola, bounded above by 2 minus y squared, the blue parabola. Once I found my x bounds, I can just project this region onto the y-axis, or you can just look for the lowest y value, the largest y value. Either way, y goes from negative 1 to 1. Okay, so those are my bounds. Now that I have my bounds, I need to calculate this gradient divided by the z partial derivative. So if I look at this equation I have for the plane, it's a plane, so the gradient is the normal derivative for the plane, or that's the coefficients of x, y, and z. But I can just as easily take the partial derivatives and see I get 1, 2, 2. Right, so that's my gradient, 1, 2, 2. This 2 is the partial derivative with respect to z, so that's what we're going to divide by. It's already positive, so I don't need to take an absolute value. I do need to take the magnitude of this vector. And the magnitude of this vector, it's all constants. So it's just 1 squared plus 2 squared plus 2 squared is the square root of 9. It's 3. So now I need to set up this integral using the bounds I found in step 1. The function I'm going to integrate, I found here. It's the magnitude of the gradient, which is 3, divided by the z partial derivative, which is 2. So I'm just integrating 3 halves. And I set up my bounds. In y, I'm going from negative 1 to 1. In x, I'm going from y squared to 2 minus y squared. I can actually factor this 3 halves out, pull it out of the integral, and then I can just subtract my x bounds, since I'm integrating 1 here. So 2 minus y squared is 2 minus 2y squared, and I just have to integrate in y. I'm going to go ahead and pull this 2 out as well, so I can cancel this denominator out and have 3 times this integral. I integrate y to get y minus 1/3 y cubed, plug in my bounds to get 3 times 1 minus 1/3 minus a negative 1 plus 1/3 times negative 1 cubed. But I work this out, it's just 3 times 2 minus 2/3. I distribute that 3, that's 6 minus 2, which is 4. So my answer here is 4. So this problem worked out nicely for 2 reasons. One reason is that my gradient was just constant, so I didn't have any functions at all. I didn't have to worry about replacing z with anything. And the other reason was that this surface was strictly above the xy plane. If I have a surface that goes above and below the xy plane, that's going to be a problem, because I'm going to end up integrating over this region twice. So that's another reason why you wouldn't want to use this method. If you have, let's say I had a sphere, right? X squared plus y squared plus z squared equals, I don't know, say 4. And I wanted to use this method, I would have to set up an integral for the piece that's above the xy plane and the piece that's below the xy plane. Although their surface area is going to be the same, right? It's just 2 halves, so you could multiply one of them by 2. But it's more to think about than just trying to find a parameterization and use that formula we had in the last video. So just some words of caution when you try to use this method for implicit surfaces. All right, the last thing I want to talk about in this video, and something I've hinted at a couple times, are ways to generalize the formulas we've already talked about. A lot of the things we've talked about in this section were either we assumed that we were integrating over the xy plane, or we assumed we were dealing with a function of x and y. But this is only one possibility. There are other simple cases where we can make a slight change to our formula and still have something similar that we can use. So the first thing I want to talk about is what we talked about in part 1 of section 16.5. If we have a function z equals f of xy, then we know we can find the surface area by integrating over some region in the xy plane, the square root of these partial derivatives squared plus 1, integrating with respect to x and y. Well, what if I have, instead of z equals a function of x and y, I have y equals a function of x and z? This is different, but it's kind of similar. So can I have something similar for the surface area without having to do a lot of work? Yes. And the key here is to think of this 1 in the z spot, and z was equal to a function of x, and the other two, I took partial derivatives. So now I have y equals a function of g. So I'm going to put 1 in the y spot, take partial derivatives of g with respect to x and z and square them. Now d is a region in the xz plane, so I'm integrating with respect to x and z. And then what if I have a function of y and z, so x equals a function of y and z, I have this surface that's only y's and z's. I can do the same thing, put a 1 in the x spot, take partial derivatives with respect to y and z and square them. And now d is a region in the yz plane. I'm integrating with respect to y and z. So you see, you can generalize what we've learned to two more easy cases. If I just have a function with x's and z's in it, I can use this formula for surface area. If I just have a function of y's and z's in it, I can use this integral to find the surface area. All right, similarly, for what we just talked about earlier in this video, the surface area for an implicit function, we assumed that we were integrating in the xy plane. But what if I have an implicit surface that isn't above the xy plane, but it is above one of the other coordinate planes? You wouldn't think above, but for lack of a better term, let's just say it's above the xz plane or it's above the yz plane. So what we can do, if I want to integrate an implicit surface over the xz plane, all that changes in the formula is now d. Instead of d being in the xy plane, it's in the xz plane, so we're integrating with respect to x and z. And instead of dividing by the z partial derivative, I divide by the y partial derivative. So whichever variable is 0 in this plane. So z is 0 in this plane, I divide by the z partial derivative. Y is 0 in this plane, I divide by the y partial derivative. Similarly, if I want to integrate an implicit surface over the yz plane, it's the same formula, but now d is a region in the yz plane. I'm integrating with respect to y and z, and I'm dividing by the absolute value of the x partial derivative. Let's talk about surfaces of revolution. So earlier, this was in part 2 of section 16.5. We talked about if we have a curve, y equals f of x, and we revolve that curve around the x-axis, then x is going to be one parameter. We make circles with the other two variables, and the radius of those circles are given by the function. But what if I don't have a function of x, and what if I don't want to revolve around the x-axis? So what if I have x equals a function of y, and I want to revolve about the y-axis? Well, now y is going to be my parameter. I'm making circles in x and z, and the radius of these circles is given by the function, etc. There are a bunch of ways to set this up. You just want to keep track of which axis you're revolving around. The other two variables are where you're making circles. So if I'm revolving around the z-axis, I'd be making circles in x and y. And you want to make sure that whatever your function is, it's in terms of the variable that you're revolving around. So if I'm revolving around the y-axis, I need u to be my y parameter. And then the radii that go with the circles come from the function. And finally, we touched on this in part 2 as well. We can have different orientations for our cylindrical coordinates. So let me just show all of them at once. This is what we're used to for cylindrical coordinates. X and y are polar coordinates, r cosine and r sine, z is equal to z. But that parameterization we saw for a cylinder going in the y direction, we had 3 cosine theta and 3 sine theta for x and z, and then y was another parameter. So that's a possibility. If you want to use cylindrical coordinates where your cylinders are parallel to the y-axis, you just let y be itself when you're translating from Cartesian to cylindrical, and then x and z are r cosine and r sine. Similarly, if you want cylinders parallel to the x-axis, then y and z are going to be in polar coordinates. So basically, whatever axis your cylinder is parallel to, and you want to translate from Cartesian to polar, that variable you keep the same. The other two variables you put in polar coordinates. And the cosines and sines, you can also switch those. So you could put sine here and cosine here, and all that does is change the orientation of your surface. We haven't talked about orientations of surfaces yet, but we're going to get to that in the next section. But for now, you can just use the last part of this video as a reference of a bunch of different things that we've already learned, just ways to generalize them to different situations very easily. And now we're finished with this section on parametric surfaces and surface areas. In the next section, we're going to talk about surface integrals, where you actually integrate different functions on a surface.